he's associate professor from IISER Pune. So he did his PhD from TEFR, and then he did a couple of postdocs, one from MPA Dresden, Germany, other one from University of Paris, Leuven, Orsay, France. And he was also visiting scientist to IFW Dresden. So his research interests include single-crystal growth and characterization of low-dimensional quantum magnets, geometrically frustrated systems, iron-based superconductors, TMDCs, and 4D, 5D type of pyrochlorides. Yeah, maybe with this introduction, yeah, I could not find many other things like your other fellowships and all. Maybe I was just I was rushing. Sorry if I ignored your.
The introduction that you gave is more than enough, actually. I'm very grateful that you invited me. I'm thankful to you and to the whole department, actually. Tanushri is there, Priya. I feel overwhelmed. I feel quite honored that you gave me an opportunity to talk about the research work that we have done here at IISER Pune. And I'm thankful to everyone who is here, including Punya, who is not from this field. You have taken time out of your busy schedule and listening to me. This really is great. And I must tell you that during pandemic, I didn't attend any online conferences. So this is my second online presentation. I'll try not to bore you too much. Please bear with me. So basically, the title that you may have seen, which was circulated, and the title flashed here is slightly different. So I'm going to talk not only on iron-based superconductors, but also on some other quantum materials where the impurities play a significant role. So this way I have widened the scope of my presentation so that it appeals to more people, because I saw that people work here in diverse areas. So that is really great. And iron-based superconductivity is something that is not really that I do on a day-to-day basis. This was one odd paper that I'm going to present here. So with this, I will start. So here is what I would like to cover in this presentation. Let's see how much I'll be able to cover. So the other quantum materials that I referred to in the previous slide are actually low-dimensional quantum magnets, spin chains, and spin ladders. And I will show you some very exciting physics that we did recently with the help of very tiny amount of impurities. I mean, how the impurities changes their spin excitation spectrum and their ground state properties. And then we will, come to the crux of this presentation, which is on iron-based superconductors. And we will be dealing with the pairing symmetry of the superconducting order parameter. And we will see how impurities, even though it's not a very strong probe, it's not like, let's say, scanning, tunneling, spectroscopy, or ARPES, which SETI does. But using the impurities, you can get some idea about the gap structure of superconductors, and especially iron-based superconductors. So let's come to low-dimensional quantum magnets. So here I show some of the crystals that we have grown here at IISER Pune. So basically the materials that are flashed here are spin chain and ladder compounds. So their chemical formulas are given over here. So I will rather focus on the crystals. So the crystals are grown by optical floating zone technique, and within optical floating zone technique, there's something very special known as TSFZ, traveling solvent floating zone, which is like a flux growth version of float zone method. So that is what we have used to grow these crystals, and we have used this method because these materials, they grow non-congruently. They don't have to really understand all these terms. So these crystals are large, as you can see, and you can see very shiny facets. So these surfaces, mirror-like surfaces that you see, are actually natural cleavage planes. It's not that we have mirror polished them. And in some cases, these are as large as the length of the crystal itself, which itself is about 6 to 7 centimeter long. So what is interesting about these materials? Structurally, they are three-dimensional, but magnetically, they are one-dimensional. So for instance, here, the blue ball represents a copper ion. Copper ion carries a spin 1/2. It is square planar coordinated, and they form a chain-like structure. And within the chain, the interaction is mediated via this intervening oxygen. So the super exchange interaction is very strong, particularly for this compound. It is of the order of 200 milli electron volts. And if you're not very well versed with the electron volts energy scale, then the approximate conversion to Kelvin would be about 2000 Kelvin. So there's a very strong interaction between the copper spins within the chain. On the other hand, the interchain interaction, which is the interaction between two parallel chains, is rather weak, about 3 to 4 orders of magnitude weaker. And therefore, these systems exhibit excellent one-dimensionality, and they are excellent systems to probe the low dimensionality or one-dimensionality of magnetism. So SrCuO2 has roughly the same structure, except that it has a zigzag chain rather than a straight chain. And because of that zigzag chain, there is an additional ferromagnetic interaction, which is mediated by this oxygen over here. So that makes its physics a little more exciting. And the third example is that of a compound which is known as hybrid chain ladder compound, because the structure consists of ladders, which are shown over here. So these are the ladders. So this is ladder number 1, this is ladder number 2, these are the rungs of the ladder, they are the legs. And these ladders are very weakly coupled to each other. So they talk to each other, but very weakly. And within the ladder, the interactions are very strong. And the structure actually consists of ladders and planes which are stacked alternatingly. And these layers are actually separated by a layer of strontium atoms, which disallow crosstalk between them. So what is interesting about this material is that the ladder sublattice and the chain sublattice are structurally incommensurate, which means you cannot fit an integral number of chain unit cells and an integral number of ladder unit cells into the same box. And this leads to buckling of these layers and very interesting vibrational properties, which is what I'm going to flash in one of the slides. So the crystal growth is described very vividly in some of these papers. So if you're interested, and I know some of you are interested in crystal growth, you can take a look at these. In the left, you see the image of an actual molten zone. So this is how the experiment works. So here is the crystal which is being grown, and here is the melt which is sandwiched between the crystal and the polycrystalline feed rod. And on the right, what you see is actually an image, optical microscopy image taken under polarized light of the frozen in molten zone to see, what is there inside when the growth is actually happening. And that is interesting because these are non-congruently melting material, as I said. So what is it that we are interested in? We are interested in looking at the excitations, as I said, and excitations in a spin chain. So here's the spin chain, antiferromagnetic spin half chain to be more specific. So this is the ground state of the chain where the spins are alternatively arranged. And the excitation spectrum looks like this. So what do you see here? You see that there is a lower bound and there is an upper bound in the spectrum. And then there is a continuum of states that are accessible to these quasi-particles. But these quasi-particles I'll talk in a minute. So basically there is a continuum. That's why it's called 2-spin-on continuum. Why it is called 2-spin-on? It is called 2-spin-on for the following reasons. So if you look at the excited state, which you get by flipping one of the spins, so let's say if you flip this spin, so the total spin quantum number changed by 1, and this 1 is shared equally by these two domain wall-like excitations. So this carries a spin half, this one carries a spin half, it doesn't carry any charge. So these are chargeless, but spin half quasi-particles. So these are called spin-ons, and their counterpart is called charge-on actually, or holon in other contexts. And you can actually see a spin charge separation on a spin chain. And recently, in fact, we have shown that you can even observe the spin orbital separation in the compound strontium 2 copper oxygen 3. Anyways, returning to this, so you can create these domain wall like excitations, and once this excitation is created, then you don't need any further energy. So the initial energy was imparted by an incoming neutron or by a small change in temperature. But if you're sitting at a fixed temperature, then the neutron can flip this spin, all right? And then afterwards, these excitations can propagate freely along the length of the chain, okay? So the lower bound of this excitation spectrum corresponds to the state where one of the spin-on is at rest and the entire momentum transfer is absorbed by the second spin-on. And the upper bound corresponds to the situation where both the spin-ons are moving in the opposite direction with the equal momentum. So the momentum transferred is shared equally between the two spin-ons, all right? And between these two extremes, there is a continuum of states that the system can access. So this is the hallmark of the spin liquid state, or the Tomonaga-Luttinger spin liquid state that one can observe in these materials. And in fact, experimentally, this has been seen both for strontium copper oxygen 2 as well as for strontium 2 copper oxygen 3. So these days we talk very excitedly about the spin liquids. Of course, we talk about different types of spin liquids. We talk of spin liquids in the Kitaev model, for instance. But the spin liquids are around since the time we know about these spin chains, and these have been seen. And this is the hallmark of a spin liquid ground state, the continuum of states that you can access in the inelastic neutron scattering experiments. And for such experiments, you need large crystals so as to have a good signal to noise ratio. Now, what is it that we want to do? We want to look at this excitation spectrum in the presence of impurities. So we work with two different types of impurities. One is the spin 0, or the scalar impurity, or a spin 1 impurity. And I'll show you in a minute that spin 0 and spin 1 are topologically equivalent. Or we work with spin 1/2 impurity. So let's look at the case of spin 0 impurity. And this is the region of the spectrum that we are exploring in our experiments. Why this region? Because you see, this is pi times j, and I told you that j is about 200 MeV. So this vertical scale is very, very large. In order to access this, you need to do multiple experiments. On the other hand, you can do very low energy experiments at PSI, Paul Scher Institute in Switzerland. So what happens with the spin 0 case? Let's return to the physics. So when you have a scalar spin, it cuts the chain into finite length segments. So basically, you will have a segment that extends from here to here, and then you will have a next segment that extends from this point till you encounter the next scalar impurity, which could be a zinc atom, for instance, because zinc carries a spin 0. So what you have done is you have divided the spin chain that initially ran from -infinity to +infinity without any loss of translational invariance into these finite length segments. And now the spin-ons are confined to these finite length segments. So basically, you have confined a particle in a box. This is analogous to the problem of quantum mechanics, first year quantum mechanics problem, the problem of particle in a box. So what should you expect? What you would expect is that this excitation spectrum, which is gapless and which is continuous, will open up a gap. So there's a gap that has opened up, and we have also shown that the size of this gap will scale with the concentration of the impurities. The larger the impurities, the smaller the length of these sections, and the smaller the length of the box, the larger the energy gap, right? So the idea is very simple. Now, the spin 1 is topologically equivalent.
Interesting. I think Professor Sahadas Gupta has a question.
Sure.
Yeah, I just wanted a clarification. So when you add these impurities, they become randomly distributed.
Exactly.
So that means your length, that will be also random.
Fantastic. This is a very nice question. I thought I'll not talk about it because I just wanted to give a glimpse of it. So yes, you will have a distribution of L. So you need to, if you want to explain this theoretically and quantitatively, you have to assume a distribution and so on. So this gap is, in that sense, soft gap, because L can vary from any value to any other value. So basically, you take a Poisson distribution for this L.
Okay, thank you.
Yeah. And now the spin 1 is...
there is one more question. So
Yeah, sure.
I think you're okay, right, for the interruptions in between?
It should be fine. I'm happy.
Yeah, Mano, please go ahead. I think you people don't need my mediation. You may directly ask.
Fine. That's fine. I think it's good to have a moderator. Okay, so I was just wondering. So it's a very similar to what Tanusriti asked. See, once you have this random impurity, then your length scale can vary from, anything more than 2 unit cell to infinite.
Exactly.
So in that case, if you have a very large chain, then again it becomes gapless. So because those numbers are those low-lying energy states are going to come down, and then it will be difficult to detect, actually.
You're right, actually. So Basically, it depends on the concentration of the impurity that you're putting. So if it is 1%, then on an average, every 100 site will have an impurity atom, right? If it is lower than that, if it is 0.25%, every 1,000 site will have. So 1,000 is an average length, but you will have a distribution, of course. And the distribution, as you pointed out, will vary. And as I said, we take it to be a Poisson's distribution.
Yeah. So basically, even if you take the 100 site, or even not even 100 site, if you take 20 site or 30 site, if it's a normal Heisenberg, your gap is going to reduce less than 0.01 J. So it's almost difficult to detect.
Yes, if J is very small, it will be very, very difficult to detect.
Yeah.
That's why these systems are very special. As I mentioned, J is of the order of 200 milli-electron volt. That's the beauty of these systems.
Okay.
And that allows you to access the low energy physics at sitting at reasonably accessible temperatures and energies.
Okay. All
right. So let's very quickly return to spin 1. So when you have a spin 1, you will form this kind of a cloud. This is basically you can think of it as a Kondo cloud. Just as the magnetic impurity in a metal gets screened by conduction electrons, so here the impurity spin will get screened by these neighboring spins, and these 3 sides will get integrated out from the spin chain. So basically, once again, it is analogous to cutting the chain into finite length segments. Now, when you put a spin 1/2 impurity in a spin 1/2 chain, you don't expect much to happen, and actually that is what you see, that there is no gap that you could open up because of spin 1/2 impurity doped in a spin 1/2 chain. So this is fine. So let's now go further. So this is something very recent. I just wanted to flash. These are experiments done in the group of Professor Srimanta Midday at IISc Bangalore. So unlike the previous case where we were working with 1% or 0.25% of impurity, here we have 10%. So it's no more an impurity. It's basically a doping experiment where you put 10% nickel at the copper side, and the experiments were done to access the orbital polarization in the nickel atom in a square planar coordination, which is related to the superconductivity in nickels, the origin of superconductivity in nickels. And we found some very interesting results. We found a very high orbital polarization. According to Srimanta, this is the highest orbital polarization ever reported. And this comes about because the nickel is effectively in a low spin state, which means that both the holes, they reside on the x square minus y square orbital of in this case. So this paper is published recently, and I'll not talk too much about it because Srimanta is the expert. He would talk to you about it someday, I'm sure. So let's look at the case of cobalt. So by the way, I didn't probably tell you that spin 1/2 impurity is realized by doping cobalt, and spin 1 is realized by doping nickel, and spin 0 is realized by doping zinc. So cobalt case, as far as excitations are concerned, looks to be very non-interesting, but actually that's not the case. So cobalt actually is different from copper. Even though both are spin 1/2, copper is actually is a spin 1/2 with an isotropic spin, because the orbital angular momentum is almost completely quenched. On the other hand, there are very old papers that tells you that in cobalt ion, the orbital angular momentum is not fully quenched, and therefore you get an effective spin 1/2, and this effective spin 1/2 is not isotropic, it's more Ising-like. So what would happen if the spin 1/2 that you're introducing in the chain is not isotropic, is not Heisenberg, but Ising-like, whereas the chain itself is a Heisenberg chain because it's made of copper spin 1/2s. So that, in fact, manifests itself very beautifully in these experiments where we have plotted specific heat as a function of temperature. And you see, this is the ordering temperature for the pristine chain. Now, why is there an ordering in the pristine chain? It is not expected to order because it's supposed to have a Tomonaga-Luttinger spin liquid ground state. Well, it orders because, as I told you, there's a finite interchain coupling. I think the experts here, they know it, but this is mainly for the PhD students. So because of the finite interchain coupling, it orders. But what is happening now as you're increasing the cobalt concentration? So you made 0.25%, 1 in 1,000 atoms. The transition temperature increased by 50%. Suddenly, there's a jump in transition temperature. And thereafter, the transition temperature is still increasing. The peak is getting more pronounced, but the increase is linear. So this jump in the transition temperature, I mean, the reason why I'm showing this inset is to impress upon you that it is not happening because somehow by doping cobalt, you have increased the interchain interaction or the three-dimensionality. Actually, something fundamentally is changing in the system when you're doping cobalt impurity. Now, what is it that is changing? So we went to the theorist, and the theorist told us that, look, this is a spin 1/2 XXZ model. This is the Hamiltonian for this model. This is the the longitudinal field. That is, the field is applied along the Z direction along which the spins point if they are completely Ising, which is the case when epsilon, which is the parameter that measures the Isingness or the isotropicness of the system. So when epsilon is 0, you realize a pure Ising limit, and in the Ising limit, the ground state is Néel ordered, and it goes into a fully polarized ordered state when the magnetic field, you go on increasing the magnetic field. On the other hand, in the other extreme, when you're sitting here, you get this spin liquid ground state. In between, there's something very interesting which is happening, which is when you apply a magnetic field, you go from a Néel ordered state into a kind of disordered state before coming out back into this TL spin liquid state, and finally under very high field you will just polarize all the spins along the spin direction. And this has been seen in one cobalt spin chain compound, barium cobalt 2 vanadium 2 oxygenate. So there are many papers on this, and this is basically what the phase diagram looks like, and these are the three phases. So you have this antiferromagnetic Néel ordered phase, and then you have this disordered phase, which is known as longitudinal spin density wave. And then you have this transverse antiferromagnetic phase. And of course, you haven't reached the field-induced ferromagnetic phase. So can we see something similar? Is it something similar happening in our case also? So we did these experiments. We applied magnetic field, and here I'm showing you the temperature derivative of the specific heat. Temperature derivative, just to make things very clear to you. So what's happening is that these experiments are done on a sample which is doped with 0.25% of cobalt. So under the zero magnetic field, this is the ordering temperature. This anomaly corresponds to the ordering. So what is happening is, as you're increasing the magnetic field, this anomaly is getting suppressed, and finally it disappears. So this is a continuation. So from 13.5 kiloesterts, this is in kiloesterts, you come to 115 kiloesterts, and as you go on increasing the field, the transition vanishes at some point around 5 Tesla of magnetic field, and thereafter a new phase appears. Okay, and this phase has the opposite characteristic of the original phase. So this phase gets suppressed by magnetic field, and this phase gets more and more profound, more and more, basically manifest itself more and more strongly as the magnetic field increases. So definitely the system exhibits field-induced changes. These were confirmed by doing neutron scattering experiments. So this is one of the magnetic Bragg peaks, which we have measured as a function of magnetic field, and this shows the transition from ordered state into disordered state where the magnetic Bragg peak has disappeared. And so this is seen for various temperatures as a function of magnetic field. It basically reproduces this phase diagram that we will generate here between the field and the temperatures of these anomalies. But one additional information which is very crucial is that this transition is very strange in the sense that it shows a huge hysteresis. So it shows all signs of disorder. So our preliminary phase diagram is shown over here. We believe that the ground state, which means the state in the presence of no field, is an antiferromagnetic state. As you apply a magnetic field, you suppress this transition, and in between you induce this disordered state, and finally before inducing an ordered state where the transition temperature increases. And this is in good correspondence with what is expected theoretically. So we need to do some more work to explore this disordered state further before we get to publishing this work. So this is all about the spin chains that I want to talk here. And now I'll go to, this slide. So this is on the hybrid chain ladder system. So as I told you, the chain and the ladder sublattices are structurally incommensurate. So what happens because of that is that the layers, the softer layers of the two, which is the copper oxide copper-oxygen chain layers, they buckle a little bit. And at low temperatures, what happens is that these two planes, the chain plane and the ladder plane, they slide past each other. And because they are slightly charged, as the compound is intrinsically hole doped, and these holes are unevenly distributed between the chain and the ladder sublattice, so therefore there's a charge on these planes, and that charge acts as a restoring force. So these planes are, they're sliding past each other. Imagine these are massive planes. So the frequency that you get for this oscillatory motion, this sliding motion, falls in the terahertz regime. So we did terahertz experiments to actually see these sliding motions. So we first got the evidence of sliding motion from the specific heat, because in the specific heat you don't expect anything at this temperature, where we see a bump here. And that if you subtract the background specific heat, you see a peak in the specific heat. This specific heat is coming because of this extra vibrational motion. And in the glass community, they call it a boson peak because of a large number of extra vibrational modes. In this case, there's one sliding vibrational mode. And then what you do is you dope impurities, and you see how the impurities would pin this motion and so on and so forth. So this is what is done over here. So this is all that I wanted to talk about impurities in low-dimensional quantum magnets. Now let's move on to the iron-based superconductors, which is what I promised.
Sorry, I'm sorry for interrupting you here. Actually, I was just wondering that you are saying the ordered phase at finite temperature in 1D, right? So what exactly that means here?
Sorry, which ordered phase in or 1D? This one you're talking about?
Yeah. At finite temperature, you are saying, is it because of the three-dimensional ordering? Because 1D you can't have.
It is because of the three-dimensional.
Okay.
Yeah. And also, since you brought me back to this slide, I wanted to point out that in the perpendicular field or in the transverse field, we don't see any change in the transition temperature, literally. So we don't see this beautiful phenomenology when the magnetic field is applied perpendicular to the chains. It's only when the field is applied in the direction of the chain that you see all these things. Okay. So I think most of you, even the PhD students, would know iron-based superconductors. Sorry, I don't know why this is moving fast. So I'll try to control it. So you must have seen these presentations, and I will not bore you because my idea is completely different. I want to talk about the appearing symmetry, but just wanted to remind you that it was discovered in 2008 and by this gentleman in his group, actually, and on this compound which is listed here. And unless you dope fluorine at the oxygen place, you don't get superconductivity. So we will see that in a minute. So these are various I don't know why this is happening. So these are various iron-based superconductor families. This slide is already from 2010. By now, I think in the last 10 years, many more other families of iron-based superconductors are discovered. So we'll not bother ourselves with that because we will be focusing on this particular family. However, let's look at the general trends, structural trends. So what you see is that these are layered materials. So what is common about all these families is that they all have this iron arsenic layer. And between any two iron arsenic layers are stacked along the, let's say, C-axis of the crystal. And then between any two iron arsenic layers, there are these blocking layers. And the complexity of blocking layers is increasing as you go towards right. No blocking layer here, where one atom blocking layer, in this case, this alkali metal, alkaline earth metal, and then you have a perovskite-like blocking layer in this case. So, I mean, these are matters of details. We will be focusing on strontium iron to arsenic 2. So you keep this structure in mind. Very simple structure, orthorhombic. And at room temperature, it is tetragonal. So A is equal to B in the basal plane. And so this is what I was trying to tell you, that this iron arsenic layer, the iron atoms, they form a square net. And each iron atom is tetrahedrally coordinated. This is important because this makes, T2G orbitals lie higher up in energy compared to the EG orbitals. So we'll come back to this picture once again in the next slide. So here basically what you see is the phase diagram, the generic phase diagram for these materials. So they show, at room temperature, they are in tetragonal symmetry. They have a tetragonal symmetry and they're disordered. The iron movements are disordered. And you start cooling it down then below a certain temperature, which is about 130 Kelvin or 160 Kelvin, something of the order of 100 and so Kelvin. It undergoes a magnetic transition. The transition, at the magnetic transition, the structure also undergoes a change, and it changes from tetragonal to orthorhombic. So in the orthorhombic phase, the A-axis is not equal to the B-axis. And in fact, the difference between A and B axis is very, very small. It's just 1% difference. And that 1% difference is apparently a huge difference in terms of the way the spins are aligned. So they are aligned ferromagnetically along the B-axis and antiferromagnetically along the A-axis. So this is the kind of spin structure that you realize. So what you see is that if you start doping it, electron dope or hole dope it, then this transition temperature, the transition from paramagnetic to antiferromagnetic or tetragonal to orthorhombic phase, it drops, and as it drops, the superconductivity appears, and the superconducting dome is shown over here. The superconducting transition temperature is maximum, and it maximizes at the point where the transition is about to vanish. So that means that the superconductivity is at its best in the closest proximity of the antiferromagnetic ground state, so or antiferromagnetically ordered state. So what it means is, or what it suggests is, that the superconductivity here should be spin mediated, okay, or mediated by spin fluctuations. But the story is a little more complex, because you have these in the tetragonal phase, these XZ and YZ T2G orbitals. These two are degenerate, and basically as you enter the orthorhombic phase, this degeneracy is lifted. So there is also a belief that this lifting of degeneracy is the driving force for the structural transition, and that naturally explains then the magnetic transition, and therefore the orbital fluctuations are very important in giving rise to superconductivity. And the blue region over here, which is the region sandwiched between the red and the white region, is known as the nematically ordered phase. So in the nematic order phase, the structural symmetry is broken, but the magnetic symmetry is not broken. The spins are still disordered, but they're not completely disordered. So there is some, a rough alignment along this direction, as you can see, but there's no long range ordering. That's why it's called nematic order. Okay. So, sorry, once again. Yeah, I mean, these are some of the initial studies that we did. I mean, as I said, we are not into crystal growth. So these are the crystals of barium iron to arsenic to dope with cobalt, which are grown by self-flux method. And then here are the crystals of calcium iron to arsenic to, and these are grown with cobalt doping. And here's the phase diagram, which looks very similar to the phase diagram I showed you in the previous slide. And these crystals are grown using the tin flux, because at that time we didn't know how to grow them using the self-flux. Barium crystals were easy to grow, but calcium crystals were not that easy to grow. But thankfully, in the calcium system, which flux you use, it doesn't matter. The properties are not very sensitive to the flux, unlike the barium case. Now, the story that I'm going to tell you actually appeared first in this PRB paper in 2018. So this is the work which is done here at IISER Pune by these three people on your screen. So this is Anupam Singh. He actually worked on the non-magnetic doping. He wrote his master's thesis on this. And Giri and Luminisa, they were actually working on the magnetic doping in strontium iron to arsenic 2. And so let me just give you a glimpse of, remind you of what magnetic and non-magnetic impurities do in normal superconductors. So on your screen, you see this S-wave superconductivity. So in S-wave superconductor, the gap is uniform all across, or everywhere, independent of the K direction. And this is the D-wave superconductivity that you realize in, for instance, cuprates, because the active orbital has the x square minus y square symmetry. So here the superconducting gap varies, of course, as you can see, and it diminishes because there's a node over here. But besides that, the phase also changes from positive to negative. As you know, that superconducting order parameter is a complex quantity. It has a magnitude and a phase, and the phase changes from positive to negative as you rotate this by a 90-degree angle. So this is known as D wave symmetry of the order parameter. This is known as the S wave symmetry of the order parameter. And what the non-magnetic impurity does can be explained on the basis of Abrikosov-Gorkov law. So I'll not go into the details of these, because these are things that you must be already knowing. So just the summary of it, that in S wave, the non-magnetic impurities are completely benign. They do nothing to the TC, whereas magnetic impurities, they suppress TC very rapidly, and this separation is given by Abrikosov-Gorkov law. The TC doesn't suppress with the non-magnetic impurities. It goes by the name of Anderson theorem. And in the D wave case, the non-magnetic impurities also suppress TC because of this factor omega sitting over here. This omega is non-zero for a D wave superconductor, and therefore you have a finite critical pair breaking rate at which the TC vanishes. Sorry about this. I don't know why that is happening. So what happens in the iron-based superconductors? So these are multi-band superconductors. Iron-based superconductors are multi-band superconductors. So this is how the electronic structure looks like. So they have a hole pocket at the center of the Brillouin zone, and then they have these electron pockets at pi 0 and 0 pi and so on. And this has been experimentally confirmed in many of the previous works. Here I've taken an image from the work of Dr. Sethi, and you can actually see the Fermi surface using the RPS experiments at gamma point here, and in the kz equal to 0 plane, and here how this evolves as you travel along the z-axis, which is not shown over here in this cartoon. So basically, it's like a cylinder. There's a slight warping, but otherwise it's more like a cylinder. So this is what it is. So these are multi-band superconductors, and this is again a cartoon, but very many experiments, mainly RPS based, and many of them where Dr. Sethi is involved, are done to show how the Fermi surface evolves as you dope electrons or hole. So as you can see, that the Fermi surface doesn't remain the way I showed you in the previous slide, which is this, but it changes as you go from here to here, which is doping electrons or holes. And what this means is that the pairing symmetry in these materials need not be same for all, which means that it can vary from one composition to another composition. And so basically, based on the last 10 years research, what we know today is that in iron-based superconductors, there are two contenders for the gap symmetry. So I'll explain in a minute what it means by symmetry and structure. So in these three cases, the symmetry is S-wave. It is S-wave because the gap, as you can see, is isotropic. All right, it's same everywhere. So same is the case over here. This is also S-wave, but the difference between this and this is that here the sign of, or the phase of, the superconducting order parameter is same over both the hole as well as the electron Fermi surface. On the other hand, in this case, the phase changes by 180 degree between the two Fermi surfaces. So these are disconnected Fermi surfaces. This is the whole Fermi surface, and this is the electron Fermi surface. And this also is a S-wave symmetry, but it has nodes. So it is nodal S plus minus wave. So this basically refers to the structure. So all three of them have the same symmetry, but they have different gap structures. All right. But this one has altogether a different symmetry, because if you rotate it by 90 degree, the sign of the order parameter changes from positive to negative. That is what you see here, which doesn't happen in this case, or in this case, or obviously in this case. So what I was telling you is that based on the last 10 years experiments, what we know today is that the gap symmetry in most of these iron-based superconductors, and particularly in the members of 1-2 family, strontium iron to arsenic 2 or barium iron to arsenic 2, is either S++ or S+-. And this you can see based on using RPS experiments, for instance, which I showed you in the previous slide, you can actually see the gap symmetry, and you can do more other more sophisticated experiment like scanning tunneling spectroscopy. You can do experiments, for instance, using Josephson junction to get the symmetry of the order parameter. NMR is a very powerful tool. So such experiments are already done. But these experiments cannot distinguish between S++ and S+-. This is one of the difficult or the hardest nut to crack, actually, whether it is S++ or S+-. And that is where, our role come into picture. Using impurities, you may be able to disentangle this S++ from S+-. This slide just tells you that knowing whether it is S++ or S+- is very fundamental, because it will also tell you what the pairing mechanism is, because S+- favors the spin fluctuation mediated superconductivity, or the glue between the Cooper pairs is spin mediated, and in the S++ case, it is the charge fluctuations or the orbital fluctuations that leads to the pairing of the electrons to form the Cooper pair. So basically, since these are iron-based superconductors are multi-band superconductors, you have to deal with a two-band model. So we can extend the Agrikosov-Gorkov formalism to this two-band model. So here, what you see on your screen is a cartoon where you have positive phase and positive phase on both the pockets. So this is the hole pocket and this is the electron pocket. In on the hole pocket, the gap magnitude is delta A, and on the electron pocket, it is delta B. All right, so delta A can be equal to delta B or not. And you can have interband scattering, which means scattering of electrons because of the presence of magnetic or non-magnetic impurities from the hole pocket to the electron pocket, or you can have intraband scattering of the Cooper pair. And same for S+-, except that here you have a positive phase on this surface and a negative phase on this surface, or vice versa. All right. Now, the question is that you can have very interesting scenarios depending on the magnetic or non-magnetic impurities. So I will very quickly summarize these. So basically, if you have a S++ situation, S++ symmetry, and you put non-magnetic impurities, there'll be no TC suppression, which is analogous to the Anderson theorem. If you have magnetic impurities, then of course the TC will suppress for both intraband as well as interband scattering. Both will suppress the TC. On the other hand, if you have S+-, okay, in this case, if you put a non-magnetic impurity, so if in the absence of any interband scattering, only intraband scattering, and there's a non-magnetic impurity, then of course the TC will not suppress. But if there's an interband scattering, and let's say if the interband scattering is more pronounced, then in that case, the gap size will start reducing, okay? And if delta A is equal to delta B, then at a finite impurity concentration, the TC will vanish. And if delta A is not equal to delta B, then the smaller of the two gaps will first vanish. And then because of the continuous interband scattering, the sign will change, and it will in fact become from S+- to S++. And such a change of symmetry has been experimentally claimed to be seen in this paper in Fitzgerald lattice. And finally, if you have magnetic impurity in S+- case, then also the TC suppresses. So basically, the point is that I know it's not very easy to comprehend these things in such a quick time, in 5 minutes. But just remember the summary of it, that using magnetic and non-magnetic impurities, you actually can find out whether it is S++ or S+-, provided you have the patience to do the experiment with both magnetic and non-magnetic impurities to arrive at the result. Just one more point, and then I'll show you some data, which is that experimentally it's not very easy to access the scattering times, which is in which terms actually the theory is formulated. So this paper from the group of Peter Hirschfeld, they actually said that you can have this delta rho, which is the change in the residual resistivity in the presence of this order. This can actually be used as a parameter to quantify the amount of disorder which is present in your system, okay, or which is in fact proportional to the scattering time. So the details you can find in this paper. So what we are going to do is we are going to show you the results in terms of delta rho versus TC. So we are going to measure the suppression of TC in terms of change in delta rho. So this is what is done here. So these are experiments which are done on electron irradiated barium iron to arsenic 2 crystals doped with ruthenium. Ruthenium is doped in order to induce superconductivity, and you can see that as you increase the dosage, which basically what this electron irradiation does is it creates defects inside the crystal. These defects are essentially non-magnetic. So basically you are looking at the effect of non-magnetic impurities on the superconducting TC. And what you see is that this is the reference sample. This is the reference sample. And as you are increasing the disorder, the residual resistivity is increasing as you would expect it to increase, and the TC is decreasing. And then what you do is you plot change in TC with respect to delta rho, and then you see how what it does with respect to the theory. And this is what the theoretical calculations are giving you. So this is the theoretical change in TC with respect to change in delta rho. And here alpha is actually the ratio of interband to intraband scattering. All right. So for instance, you can very quickly see that if alpha is equal to 0, alpha is equal to 0, which means if you put alpha, that means interband scattering is 0, then the TC should not suppress for a non-magnetic impurity, which is what we discussed in the previous slide. So now with this, we will look at some of our data.
I have one question.
Yeah, sure.
Can I ask a question? In our previous slide, the slide that you discussed, so what is the difference between reference and then
the reference is
here, the curves?
So the reference is without exposure to the electron irradiation. So which means that you are presuming that there are no defects, no impurities present. That's what reference.
But still you have ruthenium doping.
Yes, you do have ruthenium doping, and ruthenium doping is required in order to induce the superconductivity.
Yeah.
But once you have fixed the amount of ruthenium, you're not changing now the concentration of ruthenium, right? You are incorporating additional non-magnetic defects.
Okay, and irradiation, like it's a light is being shined on it.
Electron. It is done by electron irradiation. So you take it to the electron source, like at TFR, and you can bombard it with ions, or you can bombard it with electrons, and that creates defects.
Okay, I got it. So kind of like electron doping in one sense. Doping
it is not really doping. It is not doping. The electrons are not there in the sample. I mean, they're bombarded. These are high energy electrons that creates defects in the crystal.
Okay. Yeah, thanks.
So in our experiments, what we do is we dope a certain amount of cobalt, which is about 12%, and this is required in order to induce superconductivity. And in fact, with cobalt 12%, you are sitting at the top of the superconducting dome. So this is the maximum TC. And then you fix the value of X. You don't change the cobalt concentration anymore. You start changing the concentration of manganese. And you see, this is how the manganese concentration is varying for our crystals. So these are different crystals, actually. For different crystals, we have different manganese concentration, but the fixed cobalt concentration, and this is reflected also in the variation of the lattice parameters. So what we are going to do now is to look at how the TC will change when manganese, which is a magnetic impurity, goes in there. So these are some basic experiments that we have done in order to confirm that manganese is indeed there. Manganese is not contributing electrons, adding electrons to the system, and manganese has a magnetic moment which will act like a pair-breaking impurity. Will break the Cooper pair. So this is so these are the experimental results. So the TC suppresses at 7K per manganese percentage. So you can see this is the pristine sample, and as you go on increasing the manganese concentration, the TC is getting suppressed. All right. So this has been seen in susceptibility experiments where you see this diamagnetic signal, and you also see this in the resistivity experiments where the resistivity vanishes below the superconducting transition temperature. Now, what we do is something very clever. So we sort of annealed these crystals at very low not very low, but low temperatures, 350 degrees centigrade for 5 days. So it is very low to induce any kind of changes in the structure, which means to move the atoms from one side to another side. So this basically heals the crystallographic defects, the defects that you create by electron irradiation. Such defects would already be present in the as-grown crystals, and you can heal them by this low temperature annealing. And the crystallographic defects that are healed are point-like, that you can gather from this plot, where you see that the resistivity of the as-grown and annealed crystal, they just overlap each other. There's absolutely no change except for the change in TC. Only the TC has changed. So this tells you how much the crystallographic defects that are non-magnetic are adding up to the rate of suppression of the TC. Okay, so basically by doing these experiments, in one experiment we have now access to both magnetic suppression rate as well as non-magnetic suppression rate. So here you see the plot of TC suppression as a function of delta rho for as-grown crystals, where both magnetic defects due to manganese and the non-magnetic defects due to crystallographic defects are present, and in the annealed one where only magnetic defects are present. So what you see is that in the presence of the magnetic impurities, in the presence of crystal defects and magnetic impurities, the rate is 15 milli per micron centimeter, and this jumps to 350 milli per micron centimeter when you if you consider only the manganese impurities, and this is 35 milli micron centimeter. So basically a very slow suppression rate just from the crystallographic defects, and a very fast suppression rate from the magnetic defects. And this sort of gives us a clue that this is a S++ gap structure, not a S+- gap structure, because S+- gap structure should have behaved exactly in the opposite way. That is, for the magnetic impurity, this should have been much slower compared to this one. And later on, to confirm this, we did experiments with zinc doping. So zinc is a non-magnetic impurity. Now with zinc doping, what we see is that with doping with zinc actually doesn't change the TC. If at all, it increases the TC slightly. And that could be because of the varying amount of crystallographic defects that are present in these crystals. And here we see the effect of annealing. So with annealing, you see the variation has disappeared, which means that the variation was there to begin with because of the crystallographic defects. And the zinc impurities have very little, if at all, effect on the TC. And this is a very clear indicator that this is a S++ gap structure. So this brings me to the end of my presentation. The summary is here only for the second part of the presentation that deals with iron-based superconductors. So we showed that in the case of cobalt-doped strontium iron to arsenic 2, S++ seems to be the gap structure. And I mean, to my knowledge, this is the first time that someone has claimed S++ based on such experiments. There are previous experiments where S++ has been claimed for other systems, not for this particular system. And at the end, I would like to read this statement, which is from Krushnov, who did a lot of work with Peter Hirschfeld on this particular topic, impurities and gap symmetry, the relation. So he says that the gap symmetry and gap structure of the superconducting order parameter can be quite different from one material to another material. Here, by material, he means one iron-based superconductor to another iron-based superconductor. So it's not surprising that in some cases you see S+-, in some cases you see S++, and sometimes you even see a transition from S++ to S+-, or the other way around. So thanks a lot. I would like to acknowledge my collaborators, my students. The neutron experiments on spin chains that I showed you are done with Christian Hugh and Marcos Skoulatos. These were done under a Indo-Swiss research program about 5-6 years back. And terahertz experiments were done with Rajiv at IISER Trivandrum. And some of the iron-based experiments on barium and calcium that I showed you, those were done while I was visiting IFW Dresden. So I'm thankful to Sabina, Christian, and Professor Büchner. So thank you very much.
Thanks a lot, Surjeet, for the nice, wonderful talk. Yeah, already we have the question. So maybe Professor Sadhus Gupta. Yeah, please go ahead.
Yeah, I have two questions. Thank you for the nice talk. The first question is related to what you just have presented, that in one case it might be S plus minus, another compound it can be S plus plus. So which means that the underlying driving mechanism itself can be different from one iron compound to another. So is there a kind of understanding how it is related to the structure? For example, are all 1,2,2 compound are of the same class and 1,1 of the different class? Is there any such understanding?
No, actually, what we know is that that S plus plus and S plus minus are the two most probable candidates, even though you cannot rule out a nodal S plus minus in some cases. But beyond that, it's difficult. Even within 1 to 2 family, there are variations. And as I showed you in one of the recent works that is published in 2018, this PRL paper, this is from Ames lab, and Canfield and Prozorov. And they have done, again, electron irradiation in one of the 1 to 2 members of this iron-based families. And they see that even S plus minus transforms into S plus plus. So this brings us back to that very fundamental question, that what is the mechanism for the pairing in the, I mean, and how can it change, right?
So it changes as a function of what? You didn't quite elaborate. Or
Sorry.
maybe I did.
Yeah, sorry. It changes as a function of the doping concentration. I mean, if you go on increasing the doping concentration, impurities in the material, then it may change from S plus minus to S plus plus.
And my second question is it possible to, for example, like in the infinite layer nickelate, we have done some recent calculation where we strongly feel there is a presence of two gap superconductivity, in the sense that which is a orbital specific superconductivity. Possibly there are two bands and each giving rise to a different symmetry. One is a kind of a nodeless, another is with a node.
Yes.
So is it possible to kind of using such an impurity method to tell anything about it?
I don't think that impurity method in such a case will be very helpful. But yes, such cases are there. I think in cerium copper to silicon 2 also, this heavy fermion superconductor, you have this S plus ID kind of symmetry. So you
Yeah,
have
but
the,
that is bit different because then you have a superposition of the two symmetry. Here it is completely different because you have two sheets of the Fermi surface,
with
and
two.
one sheet is contributing to one kind of thing, another sheet is contributing to other kind of thing.
I see. So it is something similar to this, right?
Yes, yes,
This
exactly.
one,
Exactly.
nodal S plus minus.
Yeah, absolutely.
Yeah.
Absolutely.
Yeah.
Absolutely.
Yeah, I don't think that impurities are so very sensitive to deciphering between S plus plus and S nodal S plus minus or S plus minus. I mean, this much we could do because of this work by Peter Hirschfeld and Khrushchev. I mean, they did so much of theoretical work, and it is because of them that we have this understanding of how S plus plus and S plus minus will behave in the presence of magnetic and non-magnetic impurities. And this is really very profound. I mean, I mean what they have said, and this changed the way this sorry, I don't know, S plus minus changes to S plus plus. So they're very solid arguments that they have made for this, and experimentally has been seen. But I mean, I doubt that with impurities we can go that far. I think there are more direct tools of inferring whether you have S plus minus or not. I mean,
Yeah,
noble S plus.
I've done some, Hall experiment, and from there they try to infer something. But
Okay.
I think the major problem is the sample, because the superconductivity is seen only in one group.
Yes.
And that too in a thin film,
Thin
not
films.
in a
Yes.
not in bulk. So
Yes, that's
that I
true.
think is a very difficult
That is
situation.
that is true. As of now, this situation is very difficult in nicklets. We are also working on these nicklets, on infinite layer nicklets. We have some results, but these are all on polycrystalline samples. Nevertheless, we have some results. I will be very happy to show you those in some other.
Yeah, maybe we should discuss sometime. Okay.
Definitely. Thank you very much.
Thank you.
I have a question. So please correct me if I am wrong. You have showed me, you have showed in your presentation a phase diagram where one goes from hole dope to electron dope. Then the Fermi sheets, number of Fermi sheets, at M point also. Yeah, phase diagram relation with the Fermi. Yeah, this one. Here I see also additional Fermi pocket at the M point. I think M point or X point, what you call it as.
Yeah.
Right. So,
Well, this is a cartoon. I mean, this is just a sketch which Hirschfeld has, he has drawn mostly out of his imagination. I mean,
it's not observed.
Not imagination, intuition, I would say. So this is not based on. I mean, this is from 2011. Since then, things have changed. Your own experiments are done recently, and you have, in fact, I know, done a lot of work on how these pockets will evolve as a function of doping, right? I think in
I was thinking this is still true, So, but anyway, so now
part
the
of it
question
is very much true. I mean, these changes do happen because you're doping electrons, then you will sort of shrink the whole pocket. And so on.
Yeah. So, but with your impurity doping, in both cases, they evolve the same, like in both in whole dope system.
That is very nice. You asked this question. So we took we spent quite some efforts to prove that the impurity is not contributing any charges to the system. So these are basically localized movements. So the manganese has a local movement on it. It doesn't contribute any charge. So it doesn't changes any Fermi surface as such. So it just acts as a pair breaker. This is a magnetic movement which breaks the Cooper pair.
So my point was that you have like a hole doped superconductor and another one electron doped superconductor. Now in hole doped superconductor, you try to put non-magnet impurity and magnetic impurity, and the same the other case. So you mean to say both behave the same or different?
Right. They should behave the same. Yeah.
They should behave the same.
If they have the same S plus or S plus minus, if they have the same gap structure.
Okay, so again you are putting a question mark there, the gap structure.
Yes. If the gap structure is same, then they have to behave the same way.
Okay. Then pneumaticity, the pneumaticity has any role in this? Because electron doped, there is pneumaticity playing a role. That's what some people believe that for superconductivity.
Yes.
Pneumatic order,
I mean, I don't have a very strong opinion on this, but the pneumatic order actually puts a lot of questions about whether the spin fluctuations are more important or the orbital fluctuations are more important.
Okay, thanks. Mano, you may please go ahead. Yeah, sorry. Manoranjan? Oh.
Sorry. Yeah. So two things. Very interesting talk. One thing here, pneumatic order generally in magnetic system is very similar to like a superconductivity in the electronic system, isn't it? I mean, because here also the two magnons condensation sort of happens in the pneumatic order. Related to that, I'll come back again if I have understood this thing properly.
Are you trying to relate the pneumatic order seen here to the pseudo gap phase in high temperature superconductors, where you have you Cooper pairs, but they have not condensed?
Actually, if you see the magnetic system, generally in high field, you have some sort of magnon condensation, and just only 2 magnon condensate. And that generally they tell, just like in superconductor, you have 2 electrons condensate and forms a Cooper pair. In pneumatic order, it's the same thing. It's just magnon condensate there. So, what my question was here is, when you are seeing this superconductivity and also this magnetic behavior as we heat the sample, is it that 2 different channels are active here, or it's the same channel which is giving the superconductivity and also the antiferromagnetism?
Well, that's I think that's the key question, which to which at least I don't know the answer, and I don't think that we have enough clarity on this question. But this is a very nice fundamental question, actually. What is the role that these fluctuations, the orbital fluctuations or the spin fluctuations, and both of which are intimately connected to the pneumaticity, they have to do with superconductivity, because after all, the superconducting dome has its maximum where these transitions are also at the verge of disappearing, so they are in close proximity of each other.
Yeah.
The thing is that yes, you have spin fluctuations also because of the nesting condition, nesting of the pockets, hole pocket and the electron pocket. But at the same time, you have this this orbital degeneracy, which the system wants to lift to get over and lower its energy, so to enter the orthorhombic phase. So maybe right now, currently, there is a better understanding, because I am really not someone who is doing iron-based superconductors on a day-to-day basis.
Okay.
But from my understanding, this is still an open question, very much an open question.
Yeah, it's very amazing, isn't it? It goes directly from superconductivity to localized antiferromagnet antiferromagnetic state.
Yes, yeah, but here, if you see where you have the maximum of the dome, above this, it actually goes into the paramagnetic phase, right? Here, if you will come out into the paramagnetic phase, so you will be in the superconducting phase, then you will be in the pneumatic order phase, and then in the paramagnetic phase. So that makes you think that pneumaticity is most important, probably.
Yeah, pneumatic order is very interesting thing. People claim a lot, but experimentally it's very difficult to determine.
Yeah, that is true.
And one small question I have again is, like, all these things are like confined to the plane. Only one plane. It's not 3-dimensional phenomena.
So you mean to say in this case it is iron arsenic plane, in cuprates it's copper oxygen, in that sense? In infinite layer nickelates is the nickel oxygen plane. Yes, that's correct. But in iron arsenides, this 2-dimensionality is not as strong as in the cuprates or in the nickelates.
I see. Thank you very much. Thank you.
You're welcome.
Okay, any more questions? So I don't see any more questions. So thank you once again for the nice and wonderful talk. Yeah, it was really informative talk also.